Hello, good afternoon, everybody. Welcome to the webinar. My name is Dario Menini, and together with my colleague Paul Winnet, we're going to walk you through the following presentation. Management of the drinking water distribution networks has the aim to deliver water to consumers. Today, these systems are becoming more and more complex and more difficult to manage, due to the need of taking into account a lot of different aspects like the rise in demand, available water supply, environmental sustainability, financial considerations, and trying to include also possibly energy cost reductions. The present document contains information outlining opportunities for improving the pumping system performance, but range of application and operation for specific cases is to be deduced from our own installation, operation, or maintenance instructions, or our order acknowledgement. We are going to start talking about the components of a drinking water pump distribution system. The second part will be dedicated on the ways in which you might improve the pump system performance, starting with the design phase and, of course, the fundamental importance of a correct selection of the pump itself. And then a second part related to the avoidance of the leakages and optimization of the pumping systems. We start with the components of a drinking water pumping distribution system, which are mainly 5: hydraulic pumps, motors, piping, valves, and end-use equipment. With end-use equipment, we mean taps, tanks. When it comes to pumps, these are available in a wide range of types, size, and materials, and they can be classified into two main categories. There are two categories: positive displacement pumps and centrifugal pumps. Positive displacement pumps make a fluid move, trapping a fixed amount or volume at the suction and forcing it mechanically into the discharge pipe. Pumping action is cyclic and is mainly driven by pistons, gears, vanes, or other means, depending from the single application. This typology of pumps is characterized by a fixed displacement volume, while centrifugal pumps add kinetic energy using a spinning impeller. As the fluid flows, the kinetic energy is converted into pressure. And among the two types, the positive displacement and the centrifugal are more common due to their lower cost, their simplicity of use, their safety. Actually, other typology of systems, other typology of pumps might need more safeguards, such as many more relief valves, for example. They require lower maintenance and fewer parts have to be replaced usually. And they are characterized also by long operating life, suffering less wear and presenting a higher flexibility. We will see later that centrifugal pumps have a variable flow pressure relationship. And of course, due to this peculiarity, they can operate on a broader range of conditions. Centrifugal pumps will be the subject of this presentation. The second component is related to electric motors, and because most pumps are driven by electric motors for municipal applications. In special cases, pumps may be driven by diesel engines to allow them to operate during a power outage, for example, but the most common ones are the electrical ones. One recommendation: pay always attention to the efficiency at different loads. Another component, fundamental component of the pumping system itself is the piping. Piping, which aim is to carry the water to the point of use. Actually, there are a lot of factors which are to be taken into consideration when selecting and designing a distribution system using the pipes, for sure. Cost and material typology are two of the aspects which are taken into consideration. One of the most important factor is related to the friction losses, which is influenced by the pipe diameter, the material roughness of the pipe itself, the length, the flow rate desired, and of course about the water viscosity. There are a lot of tables in the actual hydraulic literature which are showing, for example, how a bend or a different shape of pipe might add the additional friction losses compared to a straight one. The pipe selection itself is an iterative process due to the combination which has to be taken into account by the designers of all these aspects. Just to make some example, let's say at constant flow, for example, bigger pipes are more difficult to route, but present less flow resistance at the same flow compared to, let's say, smaller pipes, which in turn are much more flexible to route and to buy because they are less expensive, but at the same time might present much higher resistances and friction losses to the passage of the water itself. Another important fundamental component of the system, the distribution system itself, are the valves. And flow in a system might be controlled by valves, which might be of different types depending on the reason they are chosen or they are meant to use. They might be used to regulate flow or to isolate equipment or to allow also water to move only in one direction. Later on, we'll be talking also about axial thrust in the systems themselves. Valve selection criteria range from the frequency with which the valve will be activated, the reliability of the single typology, the leakage tendency, the ease of maintenance, and of course also on the cost. Last component is the end-use equipment, as named before, taps, tanks, basically every latest, let's say, part of the system which represents in itself the last net loss of the water before being delivered. After this introduction, we are going to talk about on how to improve the pumping system performance. Paul?
So to improve the system performance, we need to look at the initial design stage, so the selection and operating of the correct pumps for the application, what the needs are during the operation of the pumps, and what system changes, what the characteristics of the system do, so that we can look at the pump requirements associated to the system characteristics. For the design phase, the correct sizing of the pumps is critical to ensure that the pumps are operating efficiently and to ensure that they're not oversized or undersized for the minimum and the maximum demands. The good selection practices need you to ensure that we have the correct working conditions. The mean working conditions for the pumps and the booster package are identified at initial selection stage. To design the system to take into account possible future demands, so just to ensure that we are future-proofing the equipment when it's initially installed and selected, and making sure that we have the right fit technically and economically to ensure that even though we are future-proofing the system, to make sure that it's not operating inefficiently for a number of years before it gets to its maximum of its future demand. And also to take into account any remote monitoring or condition monitoring, building management systems, SCADA systems that the package may have to communicate with going forward. If we first look at the pump selection, in many cases, pumps are sized according to the pressure and flow requirements of a network, respect to the time and day and the time of year. So quite often there will be a constant pressure requirement with a variable flow, and we need to take into account any heavy variations where there may be peaks and troughs in that demand, so as that we're evening out the operation of the pumps to ensure that the system requirements is done so that we are operating the whole package at the most efficient level, so that we're not putting untold wear and tear on the mechanical equipment, and that it is working as efficiently as possible to ensure the maximum benefit of the electricity being used to power the pumps. First, we need to assess the total head requirement of the package. So we need to calculate what we call the geodetic head, which is the residual head at the discharge point, plus the friction losses through the pipework. So we have to calculate this to the final point of discharge of the water to ensure that we get the correct pressure and flow at the furthest point from the pumps. We also need to take into account the suction height. That has to be added onto the total head. So we have the inlet height, which then will obviously benefit the suction. So that will then reduce from the actual pressure that the pumps have to produce. And we also have to take into account if there's any pressure drop on the suction when we're calculating the total head requirement for the pumps, which are the main duty pumps going forward. So if we look at the duty point, when we have all the head calculations, as the flow increases, then our system resistance increases, so we will potentially lose pressure. So we calculate for the worst case scenario so that we know that we have enough motor power and pressure in hand to give the correct performance at maximum flow that we required. So this then produces a system curve, and as you can see, as the flow increases, then the pressure increases on the system curve to overcome the increased friction loss that we have in the piping system. And then obviously in reverse, as the flow decreases, we can reduce the pressure because we have less friction loss through the pipework system, which the pumps have to cope with. So this is where we have our variable demand come in, dependent on the different pressures and flows that are required. So we can have a constant flow, but with varying different demands in peak and trough times that can increase or reduce the friction loss accordingly, which we have to take into consideration when we are designing the package. So the pumps cannot operate throughout the whole range, basically due to efficiencies, risk of cavitation. There's no fixed allowed range. However, we need to determine the operating range based upon the individual site conditions and the conditions of the actual installation and the available performance on the pump curve based upon the best efficiency point. So the duty point should lie within a range of the best efficiency points, and preferably that is within 0.7 and 1 cubic meter of the best efficiency point, to ensure that we have the lowest hydraulic loads, the lowest axial thrust on the pumps, and to ensure that we are operating the pump in the optimum position at all time. Yes, make sure that the pump is not working too much towards the left-hand side of the performance curve, because this can reduce the flow through the pump, obviously, which can create higher working temperatures and can also create cavitation within the pump. And the same goes for if the pump is working too far to the right-hand side of the curve, where again you can get cavitation within the pump again, which will quite rapidly reduce the pump life. We also need to take into account the suction conditions as well, to ensure that there is enough positive suction pressure to allow the pump to operate on its performance curve as it is designed. Again, with the wrong suction conditions, then we can also increase cavitation, which will dramatically reduce the pump components life plus the bearing life of the pump as well. It's not enough just to select the pump for the nominal operation. As I've already said, we need to look at the fluctuation in the performance. We have fluctuation potential in the positive suction head from the suction, where there are obviously varying different demands of water level. If it's in a particularly large installation, then those demands can be quite significant. And also that will then affect the suction pressure. So we need to make sure across all the operating conditions, we have the correct suction pressure to allow the pump to operate for its full performance curve. without the risk of the pump cavitating. We then have the varying of the static pressures and the geodetic head at the discharge side. Again, as we have increasing or decreasing static head, that affects the flow of the pump. So again, you'll have either higher or lower flow, which will affect the friction loss and will move the pump, the performance along the pump curve. So again, we need to ensure that those fluctuations in the discharge pressure remain working as close to the best efficiency point as we can. And also, how many pumps are in the system? Have we got pumps operating in parallel? Have we got duty standby, duty assist standby? What's the criteria? Have pumps been sized for 50% of the duty or 40% or 100% of the duty? So all these things need to be taken into consideration. And then also looking, if it is a constant pressure, varying flow demand, then possibly we should be looking at utilizing variable speed operation. Today, many pumps and booster packages generally tend to be variable speed driven as a standard. This gives a great deal more flexibility, means you can have that same constant pressure in a network with a significant fluctuating demand of flow to actually get the best performance out of the package which you're installing. So typically, if we have a single pump system, then the one pump would be designed for 100% of the duty. You may well then have a standby pump. So should the duty pump fail, the second pump will come in as a standby. However, you then kind of only don't have a standby. So many sets today, if they are probably sized at 50% of the duty with a standby pump. So at least if one pump goes down, you do have still some utilization built in, and you still have a standby pump as well. Typically within the booster set, if we look at a municipal type set, they will have WIMES control panel, they will have WIMES motors, traditionally stainless steel skid, all RAS approved to meet the water industry standards. So these are all things that need to be taken into account within the initial design criteria. If we look at single pump versus package booster sets, the one large pump can, in some instances, you will have a much higher motor power. So if we look on the slide here, you can see the one pump on the left-hand side. This is a fixed speed multi-stage pump, which would be 11 kilowatts in total motor power. So although you will then be running this unit at fixed speed, so it will have a high output current. If we go for a 2-pump set with smaller variable speed pumps, if you have maximum demand, then you will be drawing the 1.1 kilowatt equivalent of the fixed speed pump. However, where you have fluctuating requirements, where you have much lower water usage at certain periods of the day, you may only need to have one pump running. So rather than having one pump running intermittently with an 11 kilowatt motor, you could have one pump running with a 5.5 kilowatt motor, which is turned down just to meet the system demand. And then if there's a peak demand, we'll call in the second pump. And generally what you tend to find is even when both pumps are running, they're generally not running at full speed. You'll probably have one running at full speed, one running at 70% of its load. So there is still an energy saving to be had with a 2-pump variable speed system, even if they're running at very close to peak flow. And just remember to double check the maximum flow for the single pump operation to ensure that that stays within the performance curve of the best operating window of the pump. So again, if you do have a single speed fixed speed pump, there is the risk when you get to that maximum demand with changing conditions, then you could possibly run into problems with cavitation or maybe the pump running off the end of the performance curve. If we then look at introducing variable speed drives, these generally are for systems with high annual operating hours, with fixed pressures with varying different flows, and we just need to ensure that the duty points provided by the system need to be adjusted and controlled so that we fit the instantaneous needs to ensure that even at peak demand, the pump is capable of running at full speed to hit the peak demand and then can be slowed down accordingly to the off-peak periods as well. So traditional control methods, generally we would have used valves, closed-off valves, whether they're mechanical valves or electronic actuated valves. We would traditionally also use bypass lines, simple pressure switch control, varied to variable speed control. What you tend to find if you were oversizing the system, this would create higher energy bills, higher maintenance costs, system wear, and less reliability for the system versus a variable speed drive. So with the variable speed drive control on the package, you have a lot more flexibility. The pumps only run at the speed required to hit the demand required at any given time, whereas with the other three kind of methods of control, there's a significant amount of wasted energy. By pumping to bypass, throttling the pumps back along their performance curve will obviously cause the pump to have a much harder life, a lot more wear and tear on the system. And with your traditional on-off control versus soft start, which a variable speed drive gives, you have a significant amount of start current, which obviously gives you a significant peak on your electricity supply for having pumps stop and starting constantly. So potential savings within the pumping system, up to 40% of the savings could be reached through using higher efficiency equipment and variable speed drives. Also, 10% could be raised just for increased efficiency, ensuring that pumps are working more on their performance curve. And then the rest of it, the following remaining 60%, this can be really looking at your system optimization. So ensuring that everything is sized correctly on the system, valves are in good working order, and just ensuring that everything is working in the correct manner, everything is designed effectively, and we are optimizing the system and the network to ensure that we have minimal friction losses, and that the pumps are running as efficiently as they physically can using variable speed drive technology. If we have a look at the impact of variable speed drives versus the total life cycle cost, in fairness, there is a higher initial capital investment. There's a higher investment because you have the added value of the variable speed drive, the associated controls and transducers. However, we can see a reduction in energy costs between 55 and 75%. So as a result of this, because the pumps then are running at slower speeds, are running at the optimum efficiency as much as they can, there is less wear and tear on the mechanics of the pump system. We have less water hammer going through the system, because if you look at if you compare to a traditional fixed speed installation, when a pressure switch would traditionally ask the pumps to switch on, there would be a significant surge of pressure going through the pipework. This would cause water hammer, which has an impact on pipe joints, valves, other control equipment, etc. So with having the soft start of a variable speed drive, we can reduce the maintenance costs in the region of 20 to 35%. And this gives us a significant life cycle cost saving, mainly driven by the maintenance, operating and energy costs that we see and have previously explained. If we look at the fundamental rules, the reduction in speed provides significant energy savings, even at partial load. These energy savings are relevant because of the fundamental rules how centrifugal pumps operate. So if we reduce the speed, lowering the flow according to a linear function, reduction of the head according to the quadratic function, and a reduction of the power to the cubic function. So you can really see here that the significant saving is within the power consumption. So if we lower the flow, then the more we lower the flow, obviously the pump comes back along its operating curve, so therefore drawing a lot less power. So, but the power is reduced by the cube. So potentially you take a 4 kilowatt motor running at full speed, and then this could come down to one kilowatt. So there's a significant saving. Obviously, the higher the motor powers, then by the cubic function, there's a much larger power saving to be had in these instances. The aim, obviously, of using a variable speed drive is on a constant pressure system is to actually look at produce the system curve. So the aim is to keep the pump running at as close to its best efficiency as we can. The duty point should be selected slightly to the right-hand side of the best efficiency point at maximum speed, which then gives us a much larger operating window for the pump to work within. So if we have maximum flow at the pressure required for the maximum demand on the system, and that's to the right-hand side of the curve, assuming that the system is only designed to run maximum flow at peak demand, then you'll probably find 70 to 80% of the time there's a power saving to be had because the pump is running more towards the left-hand side of the curve, thus saving motor power. If we look at constant flow, then again, you would select the duty point slightly to the left of the best efficiency point. This would then give you an operating window where, dependent on the pressure, that would be then where the savings to be had. So although the flow remains constant, the pump will increase and decrease according to the requirements and the losses in the system at that given time. So if you are having things like a washdown system where you had multiple guns but needed to give a constant flow, then this would be where you would need to increase the pressure to cope with the increased friction loss through the system. But you would just say, okay, I'm set to this constant flow and I need to ensure at the furthest point this is the flow I'm getting. So it would just increase or decrease in speed accordingly to overcome the friction losses within the system. And then if we look at the potential energy savings to be had, again, this chart kind of shows an 11 kilowatt unit running at continuous operation with varying different capacities. So you see the total motor power is 11 kilowatt running at 100% load. Based on the amount of hours that this unit was running over a period of 1 year, you can see it for 55% of the year, it only ran at 25% load. So there was a saving of 4 kilowatt per kilowatt hour over that period. 25% of the time, there was a saving of 4.4 kilowatt, and it was only at 10% of the time it ran at 100% load. So you can see over the period of a year, based on the country that was operating, we're paying 10 cents per kilowatt hour. There was a reduction in energy saving of 3,200 euros per hour per year. So this was a significant energy saving just based on an 11 kilowatt motor. So the payback time on this installation was less than 1 year. So that was a good case story to get some capital investment to upgrade this plant from a fixed speed traditional pump to a variable speed driven installation. So other advantages, as I've already touched on, of running a pump at reduced speed using variable speed drive is the avoidance of water hammer. So you don't get any huge surges of pressure going through the system. Basically, because the pump works in a soft start, the variable speed drive comes in as a soft start function. You get a much larger extension of the lifetime of the pump due to the bearings and the other system components. Again, using the soft start philosophy, there's a lot less wear and tear. The motor kind of comes up to speed gradually over a short period of time. The water hammer has a lessening effect on all the other parts of the component system. So your bearing life is greatly increased, and so are the other system components. Also, the variable speed drive gives you much more flexibility when linking to other sensors and building management systems. Today, many variable speed drives on the market will link directly into a building management system, or you can plug in other sensors, transducers, flow meters, temperature gauges, etc., where you can have a lot more control over how the pump actually operates. And you also have the ability with the variable speed drives to build in redundancy into the system. So you can have pumps only running at 50% speed versus 100%. So you can have more intermediate operation rather than everything running at full speed.
Thank you, Paul. And we continue with the second part on the ways in which you might improve the system performance, how to avoid leakage and optimize the pumping system itself. We go on actually displaying the fact that, as we already said, pump of a size it might be due to the need to withstand peak loads. Actually, this is meaning higher operating costs, as correctly already displayed by Paul, higher wear on the pump itself and on all the other components of the system itself, as excessive flow energy is forced into the systems, creating unnecessary wear on valves, piping, and also piping supports. Pumps are rotary equipment and are subject themselves to wear, erosion, before we're talking about axial thrust, cavitation, leakage. Many problems may derive from a non-proper selection and operation. One of the first signals of such a defect in terms of sizing is the requirement of excessive maintenance or leakage, as we were talking before. Basically, we are talking about defects that may cause issues due to inadequate support, vibrations, valve problems. And specifically, when talking about piping, this is one of the several components of a system itself. As we already explained before, the piping configuration selection and sizing is an iterative process which takes into account the cost, the materials, but also all the sizes available in the market itself, which in turn might bring some advantages and disadvantages at the same time when compared one to the other. We remember that at the same design flow, larger pipes might have less friction losses compared to smaller ones. But on the other hand, they've got higher material installation costs. Actually, the performance is actually the ways in which you can improve the system is determining the proper size, trying to minimize as much as possible the pressure drops along the way. The flow will face pressure drops, which should be prevented as much as possible. The selection of low loss components, keeping the pipes as linear as possible, putting all valves and equipments in line with the pipe run. All these are methods and means through which you lower down the actual required head by the system itself in order to operate correctly. Before now speaking about specifically about the pumps, we were speaking about that the pump performance might be lowered also by a number of losses in itself, in the impeller, in the casing, which might be mechanical and hydraulic, both affecting flow, head, and power consumption of the pump itself. So all the performances. The mechanical losses are due to the friction with the cam coupling and the mechanical parts, while the hydraulic ones are all the obstacles that are met by the fluid during its path. Basically, we're talking about flow friction, recirculation, as it was named before, and actually also internal leakages and backflows. Actually, backflow is one of the key elements through which each and every hydraulic can lubricate itself and all the rotating parts of the hydraulic itself. This must be granted on one hand, but on the other hand should be limited to the minimum. When you make a system assessment, you may find different issues: inefficient pumping system operation, excessive maintenance requirement, erosion of components, and cavitation itself. This is mainly due to the fact that pumps in reality run far from their best efficiency point, and the material selection might not have been adequate to the application. On the right-hand side, you see a graph in which it's displayed the possible issues and behaviors of the pump along the curve itself. As you can see on the right and on the left, there are similar issues, which might be named also cavitation itself, due to the vibration of the components and of course to the rising of the temperature. When there is an oversized system, there are a lot of signs which can witness that. Correct oversizing, the correction of the oversizing can really result in a cost-effective procedure. Pipe vibration can accelerate system wear and wear also the mechanical joints of the piping. The excessive flow noise is one of the main signals and is typically the ones to which operator get used to. You think you have a very, let's say, noisy system and get used to the sound itself of it. Actually, we know that cavitation looks like some stones inside the water. It has got the same noise effect. Highly throttled control valves means that you change continuously the back pressure to which the pump is exposed to and for which it's been designed. So a restrictive position of the valves on top of the wear can cause issues because pumps run very far from the best efficiency point at which they've been selected. Another signal is the heavy use of bypass lines used for pumps which are used in order to make the pump run at their correct duty point, let's say, but with enormous amount of energy, which is essentially wasted, and a subsequent erosion of all the components of the system. Frequent replacement of bearings and seals might be witnessing the presence of a vibration and a consistent degradation of the system itself. Same thing for intermittent pump operation. You energize and de-energize continuously a system, actually making the system face the axial thrust and all the inertias due to the starting or stopping of a system, and at the same time making it stood by the axial thrust and radial thrusts of the hydraulic, and also to all the bends of the piping, for example. Not even mentioning the effort by the motor. There are some remedies that you might use in order to overcome this issue. One, as Paul already explained before, is the adoption of a variable frequency drive. You can lower down the efforts to which the system is exposed, reducing the water hammers, and you can also reduce dramatically the costs associated to the running of the system itself. A similar, not reversible action, or that of having a parallel a curve which is parallel but let's say offset downwards of the full speed one, is reducing the diameter of the impeller itself. Last but not the least is the possibility to think about a smaller pump or a booster set which might couple more than one pump, one duty and one standby each time, and occasionally working together in the period of the peak of the performance required. Pump operate better if they operate when the inlet flow has a uniform profile, so the system should be designed accordingly to enable the pump to work efficiently. efficiently. Suction pipe in the configuration is the part in the layout of the system, is the part which is the most important one, the more critical. That's the reason why, in order to enable an even and uniform inlet profile, suction pipe should be at least one size bigger than the pump suction itself. We should take into account the possibility to have a flow speed which should not exceed 1.52 meters per second. These are generic guidelines and values that we give in order to drive your selections. We are at your own disposal in order to study each and every single application. Minimum flow speed should be higher than 0.5 to 0.7 in case of a trained air or gas, while in case of solids or sediment, the flow speed should be higher than 1.5 meters per second. Pipe lengths at the pump inlet should be as short as possible in order to minimize friction, which might eventually damage or complicate the suction side of the unit itself. The pumps are to be placed as near as possible to the pump sump, tank, or eventually the source of water. If you reduce to the minimum the amount of friction losses which might be met along the way, in order to minimize the losses, it would be ideal. In open systems, the inlet into the pipe should be protected from external contaminations by a suction strainer with a corresponding mesh in order to avoid any possible solids coming in contact with the hydraulic itself. Valves at suction side must be designed in order that they release the full flow cross section at full opening. Again, in order not to dissipate the energy which has been used in order to pump the liquid. Air pockets are a risk for the mechanical seal area. So that's the reason why some air might rest in the higher points of the system and reduce the free space for the flow, causing additional losses and reducing the pump flow. So that's the reason why in all the systems, some gas traps might be eventually foreseen, but in any case, especially at the suction, we should try to avoid as much as possible that the design conditions are changed also along with the time. Other considerations for the suction side is that you should have at least a pipe of a length of 10 times the diameter of the pipe, free of any disturbance, in order to have a uniform flow. If it's not possible, at least 5 times the diameter of the pipe. Try not to mount elbows directly at the pump inlet, always for the same reason, in order to avoid that we have a flow which is not uniform, which might cause turbulences or in case also some further recirculation. Here are a couple of examples of proper installation conditions with some crazy piping. In this case specifically, there are 2 examples. The one on the left, where basically there is no reduction at the inlet. There is no valve before the outlet itself, and there is no reduction before the bend. On the right, you do have elbows directly at the pump nozzles, which should be avoided. Again, for the suction side, in case of negative suction piping should be mounted inclining 5% towards the pump, again, to avoid air, gas pockets. Possibly require reduction might be executed eccentrically, again, in order to avoid the bursting of air. Non-return valves to be positioned at the suction side in order to not to lose the priming. And at least the straight pipe from 5 up to 10 times the diameter of the pipe itself. When we are in case of positive pressure at pump inlet, income piping should be installed declining 5% towards the pump. Or we want to get rid of the air in the most convenient way. So in this case, towards the inlet. Possibly required reductions can be designed concentrically as well as eccentrically, and no return valve shall be installed at discharge side in order also to isolate the system in case of need. When using several pumps in parallel, every pump shall be executed with a known suction piping, and common suction side manifold piping for several pumps should be avoided. If you need to, at least try to respect a minimum distance among the pumps, minimum 5 times the diameters from one pump to the other, 3 times the diameter of the pipe from the first elbow. This is a case which happened in reality. There were 2 quite big pumps, more than 200 kilowatts, multi-stage ones, horizontal multi-stage pumps. They were not performing adequately, not as per the design of the system itself. Well, just inclining them and providing an adequate feeding to the pump, we were able, and which is the configuration on the right, we were able to solve the issues. This was a very cheap way through which we were able to solve a big problem. We've been talking about system problems. One of the most annoying and expensive problems that you can meet on a system is the unscheduled downtime. Basically, as we said, centrifugal pumps are much easier to operate compared to other typology, but basically they require low maintenance, a lower number of components which shall be substituted or replaced with the standard maintenance. Basically it must be scheduled, because if it's not done regularly, or the system design doesn't allow the pump to operate in the optimal condition, that might bring to unscheduled downtime. There are a lot of different, let's say, possible schedules that you might have in your own application, because each and every application might be different from one to the other. Basically, the typical maintenance is consisting of on the check of the sealing and the bearing lubrication, the check and a possible replacement of the wear parts, impellers, wear rings, check of the pump motor alignment, the leveling of the basement, and then among pump and motor itself, and then the motor itself conditions. Basically, all this can have a very varied time frame when it comes to mean time before the different actions. When we are speaking about centrifugal pumps, we are talking about 6 months, 1 year, but it heavily depends upon the single application. Preventive maintenance is key to minimize unscheduled downtime, and we strongly invite you to find also agreements with your local providers in order to make it secure. So I think that we can close the session here.
Yeah, I think so. Thank you very much for everybody's time. I hope it's been informative. As I said, if you have any further questions or would like any further information with regards to the topics we discussed today, or Xylem products or Xylem's package solutions, then feel free to reach out to your local Xylem representative. Thank you very much.
Thank you very much. Bye.